to you with this review of your midterm one most missed questions. I'm going to go over all these. I just did a quick check to see what was missed most commonly. So, which of the following, first I have to move this. This is right in the way here. How can I move this? Which of the following are Michaelis-Menten processes that have an affinity and a capacity? So which of these are Michaelis-Menten? Okay, passive absorption. Passive right away means not Michaelis-Menten because passive does not require a carrier or it doesn't have anything that can be overwhelmed. So it does not have a capacity and affinity. So this is a no. Pharmacodynamic Emax model. Well, yeah, the pharmacodynamic Emax model is about the interaction between a drug and a receptor, usually, or a drug and something that causes the effect. So it does, and remember, it does have a, can I write right on here? It does have a, the thermodynamic Emax model is E is equal, the effect is equal to Emax times concentration all over C50 plus concentration, right? So this is the Michaelis-Menten form, isn't it? Here's your capacity and here's your affinity constant. How about plasma protein binding? Same thing. Yes, there are. So this is true. This is not true. Plasma protein binding, same thing. We have a fixed number of protein binding sites. So we have N total times concentration all over KD plus concentration for our binding model. So this also is a Michaelis-Menten form. How about small drugs passing across loosely knit membranes? No, this again is a passive process like absorption, so this is a no. So it's just those two. Choose any or all of the following that could affect FA. Well, remember FA is the fraction absorbed, so it's going from the gut lumen. This is the gut lumen, so down comes the solution with the drug in it, and it needs to get absorbed into the gut wall. So this is the gut wall. So it needs to get, and this usually is done through passive diffusion, right? So plasma protein binding, are we in plasma at this point? No, this is just in the small intestine. So plasma protein binding does not affect FA because there's no plasma protein binding going on at this point. How about complexation with compounds in the gut? Sure, it could complex. That's what we see sometimes with the divalent cations. Also, we could have gut microflora changes that will change the capability of a drug, could destroy a drug before it gets into the gut wall. So that's one too. P-glycoprotein, that's in the gut wall. So once you've made it to the gut wall, yes, P-glycoprotein could affect it, but that's affecting your fraction that escapes the gut metabolism, FG, as are the CYP3A4 enzymes. They are both in the gut wall here. So these affect FG, not FA, right? All right. Oh, this one's gonna take us a minute because this is our using our trapezoidal rule to figure out our area of the curve. So It has an area under the curve when given a 500 IV milligram dose has an area under the curve of 143. So please determine the bioavailability for an oral 250 milligram dose. So we're giving half the dose when the following concentration time data is determined. So at time 0, the concentration is 0. At time 2, the concentration is 12. And at time 8, the concentration is 2.4. Notice I always draw a picture because I have to see what's going on. So we're going to make our trapezoids here. We're going to have 1, 2, and then we'll have our tail here that we'll have to look at because we're going to go to infinity and beyond, right? This is our Buzz Lightyear. We have to compare apples to apples. So for our first, which is a triangle, not a trapezoid, our width of our trapezoid is 2. Our height is a midpoint between 0 and 12, which is 6, right? So 6 times 2 is 12. So the area of that first trapezoid is 12. Our next one, this is not done to scale, of course. Our width is going to be 6, right? Because we're between 2 and 8, so it's 6 hours. And our height is the, just getting my calculator out here. The height is a midpoint between 12 and 2.4. And so it's 7.2. So 7.2 times 6. 43.2. So far we've got 12 plus 43.2. So the next thing we have to do is figure out the tail. And remember, the tail is our last concentration over K. And our last concentration here is 2.4 divided by K. So what's K? Well, K is ln(C2), which in this case is going to be 2.4 minus ln(12). And what's the difference in time there? 6, right? So doing my math here quickly. So I got a negative 0.268. So K is 0.268 per hour. So that's going to go back up here into this. So it's 2.4 divided by 2.68. And I got 8.95. So this is 8.95. So that plus 43.2 plus 12, because we're going to add all the pieces parts together. So we got an area of the curve for 250 PO to be 64, 0 to infinity. 0 to infinity is 64. What is it? 0.15, and the units are milligrams per liter times hours, right? So we still don't know our area of the curve. Now what I usually do is double this number because we only gave 250 here and we gave 500. But if we want to leave it in the form that we're supposed to, well, I'm just going to do that. Okay, so 64.15, it's just a little easier instead of doing a compound fraction. Times 2, because we only gave 250 milligram oral dose and we're comparing it to 500 IV. So we're going to compare our area under the curve for a 500 milligram oral dose is 128.29 milligrams per liter times hours. That's just 2 times our 64.15. And, well, I'll make this 3. Okay, 128.3. Boy, how do I always make things so you can't read them? 128.3. And we're going to compare that then to what we got with our IV with 500 milligram dose IV, which is 143. So 128.3 divided by 143, that's going to give us our F, isn't it? I got 89.7. So we're going to round to 2 decimals. So I guess I got, well, I'm not sure if we're supposed to see. Now this is confusing to me. So I don't know if I should say 89.7 or if I should say 0.9. In either case, I would have given you credit. So good. All right, we'll move on. New drug Shazam, see attached graph, has a therapeutic range between C20 and C80. So our concentration, or our concentration where we get 20% of the effect. So our concentration is going to be 10 milligrams per liter. And C80 is, well, you can't, I'm sorry, about 25. And we're achieving a CSS max. At steady state, we're achieving a maximum of 20 milligrams per liter. And the half-life is 8 hours. What will be the longest dosing interval possible if the concentrations are to stay within the therapeutic range? Well, if we're at 20 for our CSS max, the lowest we can go is 10, and that's 1 half-life, right? So we need to know the half-life, and there it is, 8 hours. So the answer is 8 hours. Given the following information, determine the C25 and the C50 for drug Velmorox. Please round to the nearest whole milligram per liter. So good news, we have a gamma of 1, which means we can use our Emax model. Our Emax is 100. Our C50 is 25 milligrams per liter. So what would be the concentration at, now remember we want a concentration at 25% maximal effect. So we're going to use our Emax model. Emax times concentration, C50 plus concentration. So for when we want to know our concentration at 25% maximal, we're going to put 25 in here because we want to know the effect at 25% of 100, which is our Emax. We're solving for that concentration. Our C50 is given at 25 milligrams per liter. And we're going to just solve for C now, aren't we? So what's 25 times 25? I think I know, but I'm going to put it in here anyway. So it's 625 plus 25C. You see, I just pulled the denominator over there, is equal to 100C. So I'm going to subtract, get the C's isolated on one side. So I'm going to have 625 is equal to 75C, and then just divide 625 by 75, and I got a concentration of 8.33. So it's going to be nearest whole milligram per liter, so it's going to be 8, isn't it? Now for our other one where we're trying to get C75, we're going to do the same thing, only this time our effect is going to be 75. Emax is 100. we're solving for that concentration. Our C50 is still is 25 milligrams per liter because that's the model. So 25 times 75 is 1,875 plus 75 C is equal to 100 C. So again, we're going to isolate our our C's. 75 is equal to 25 C, and so then we'll just divide 1875 by 25, right? So I got a concentration of 75. So this one's going to be 75. Did I do that right? Okay, good. Next. Your patient is on drug F. Okay, so we're focusing on this. And a CYP2C9 inhibitor, amiodarone, is added. Okay, so a CYP inhibitor is going to decrease the intrinsic clearance because our drug is metabolized by 2C9. How would you change the dosing regimen to compensate? Okay, so first I should have noted these are all telling us they're all totally cleared by the liver, we're going to assume. So our hepatic clearance is our total body clearance, and therefore our hepatic clearance is 4 liters per hour, right? It's metabolized by 2C9 and is given orally. So if we give an inhibitor, we want to know if we need to change our dosing regimen. So if our first thing we have to do is find out, we know that it's totally cleared by the liver. So is it a high or low E drug? How do we determine that? Well, we look at our hepatic clearance. We know that it's determined by Q times E. We're trying to figure out this E. We know that our hepatic clearance is 4 liters per hour, and a Q is 90 liters per hour. Our E is going to be relatively small, isn't it? So 4 divided by 90 so our E is 0.044. Okay, so it's a low E. So what does that mean? That means that our clearance is approximated by enzyme activity and binding, doesn't it? It also means that the fraction that escapes the first pass effect is pretty close to 100%. So we're going to make those assumptions because it's a low E drug. So it's being given PO. So we want to see what's going to happen then if we decrease our intrinsic clearance. Should we make changes in our dosing regimen? Well, the first thing we're going to ask ourselves is what's happening to our CSS average. What we really want to know is what's happening to our free concentration. Do we need to look at free in this case? No, we can look at total to reflect free because the only difference between free and total is that fraction unbound. And as long as that's staying steady, we're okay. So we are being given this orally, so we have to think about our bioavailability. We know more than just bioavailability, though. We know FA times FG times FH, which in this case is approximated by 1. We know that here, times our dose rate divided by our clearance. And our clearance is determined by enzyme activity and binding, right? So what's happening? We have a decrease in our intrinsic clearance. Our CSS average will increase. Therefore, we want to decrease our dose rate, right? How about our dose interval? I'm going to skip and look at half-life here. Half-life is determined by volume and clearance. We know for this drug, clearance is determined by intrinsic clearance times fraction unbound. We know volume distribution is all about binding, don't we? So those will cancel. But what's happened here? Again, we're talking about a decrease in intrinsic clearance. Therefore, our half-life is going to increase. So we're going to want to increase our tau. So I would suggest decreasing the dose rate and increasing the dose interval because of that decrease in clearance. Drugs with an FE of 0, what does that mean? FE of 0 means totally cleared by the liver. And high E drugs are always have a relatively small F because FH, with drugs, okay. So with drugs that with an FE of 1, and when they're high E drugs, they always have a relatively small F because FH, this is true, right? You can't, because when the drug comes into the liver, very little makes it out, right? Because it's a high E drug. So right away, remember bioavailability is all about the slowest guy. We know FH will be small. Therefore, bioavailability will be small. That's one way you can look for a high extraction drug, is that the bioavailability will be low. And you'll have to give a much higher oral dose than IV. So this is true. Okay. Okay, we're back to hepatic clearance problems. Those were the ones that were toughest for everybody. These are hard, and they take a lot of practice. So your patient's on drug Y. So let's, before we even go on, what's going on with drug Y? Drug Y is totally cleared by the liver, because we know that because of here. It has a total body clearance of 12.7, therefore the hepatic clearance is 12.7. So first thing, we know we're going to need to determine if this is a high or low extraction drug, right? So we're going to use our clearance is equal to Q times E. Our clearance here is 12.7 liters per hour. And our Q is 90 liters per hour. So we need to solve, I can tell it's a small or low E, right? 12.7 is much closer to 0 than to 90. So the E here is 14.4. So it's a low E. So we have the same circumstances before. And you can tell here if you look, so this one obviously, drug X is a high E drug, isn't it? And you can see it has that low bioavailability versus our low E drug. So anyway, so getting back to the problem, we're dealing with a low E drug. Drug C has a lower KD for AAG than does drug Y. So a drug C is being added that is going to have a higher affinity for the protein than our drug Y. So what's going to happen? Well, there's going to be an increase in a fraction unbound of our drug Y, because it's going to be displaced because that KD, the affinity for the AAG that we're vying for, is lower for this new drug that's being added. So in this case, since there's a change in fraction unbound, change in binding, we need to look at CSS free, because it's going to be different than total, isn't it? So CSS free is equal to, again, it's being given how? Orally. So we have to think of FA, FG times FH, which is approximated by 1 for a low E drug, times your dose rate, all over clearance, which in this case is intrinsic clearance, times fraction unbound. We have to multiply the whole thing times fraction unbound to look at free concentration. So even though the free fraction is increasing here, these two things will negate each other, and there will be no change in dose rate. So we don't want to change, or there'll be no change in our free concentration at steady state. So we don't want to change the dose rate, right? How about dose interval? Dose interval is going to be 0.693 volume over clearance, which for this drug is intrinsic clearance times fraction unbound. But remember, we know that volume of distribution is all about binding, isn't it? So what you will see then is that these fraction unbounds cancel because that increase in fraction unbound increases both volume and clearance to the same extent. So again, no change, and we're not going to change the dose interval either. That's why we have to be very careful. What will happen to total? Just so if we forget about this, what's going to happen to total? Total is going to decrease, isn't it? And when we see that coming back from the lab, we're going to want to increase the dose rate, but we should not. We should leave it alone because we care about what's happening with free, not with total. It's a tricky one. All right, now we have drug X has a lower than normal albumin. Therefore, the fraction unbound of drug X is increased. So we have an increase in another binding change. These are tricky. Drug X. Okay, let's look at drug X here. Again, cleared by the liver, bound to albumin, highly bound to albumin. Here we have a high extraction drug, right? Look at that bioavailability and look at that clearance. So our clearance in this case, which is 72 liters per hour, is equal to 90 liters per hour times E. This is clearance. It's equal to Q times E, right? Just so you know what I'm doing. So 72 divided by 90, that's going to be a very high. Okay, so this is an E of 0.8, isn't it? So this is a high E drug. So in this case, clearance is approximated by Q, and the fraction that escapes the first pass effect is approximated by Q over intrinsic clearance times fraction unbound, but this fraction unbound is seen as 1 because it's non-restrictively cleared. Well, praise the Lord, we're going to give this IV. Okay, so let's look at our CSS average. Do we need to look at free or total? The only time we need to look at free is when there's been a binding change. Has there been a binding change? Yes. So we have to look at free concentration. But it's being given IV, so we can skip the bioavailability part and just have dose rate over clearance, which is Q in this case, times the fraction unbound. What's happened? The fraction unbound has increased. Therefore, our CS average will increase. So we want to, therefore, decrease dose rate, don't we? So we're going to decrease the dose rate. How about dose interval? Again, half-life of this drug. What's happening? We're going to have an increase in our volume, but no change in our clearance. So we're going to see a longer half-life. So we're going to want to increase that dosing interval as well. Okay. We're getting a workout here. Patient on drug H. Okay, let's take a look at H. It's cleared by the kidney, or I'm sorry, totally by the liver, not cleared at all by the kidney. Highly bound to albumin, high E drug, given IV. You can see again a low bioavailability. So this is a high E, so clearance is approximated by Q, and fraction that escapes first pass effect is determined by Q over intrinsic clearance times fraction unbound, which is really seen as 1. Okay? Now, how did I know that? Again, clearance is equal to Q times E. And so we know this. We just did it in the last one. Okay. So has poor nutrition resulting in a decrease in albumin? So what's happening here? A decrease in albumin will result in an increase in fraction unbound. This is actually the same situation we just did, isn't it? So how would you suggest adjusting the dosing regimen? All right, well, again, we need to look at free this time, don't we? Because we have a decrease in albumin, which will increase the fraction unbound. So we've got an increase in fraction unbound. So since there's a binding change, we need to look at free. Again, it's being given IV, so we don't need to worry about bioavailability. We have dose rate over clearance, which in this case is Q, times fraction unbound. And what's happening? Our fraction unbound is increasing, so our CSS average will increase. Therefore, we want to decrease our dose rate, don't we? And how about half-life? Half-life, 0.693. Volume, which we know is determined by binding all over clearance, which is determined by Q in this case because it's a high E drug. What's happening again? There's an increase in fraction unbound, which increases our volume. Therefore, we have an increase in half-life, so we're going to want to increase our dosing interval. Okay? That's it. Thank you for your time. Hopefully this helps you in getting ready for either the golden ticket for midterm 1 or studying for the final. Thanks so much for your attention. Bye-bye.